So, we have seen this susceptibility for paramagnetic material is C by T. C is Curie temperature and C basically C equal to n mu square by 3 k V, then here mu 0 right. For chi for ferromagnetic, that is C by T minus theta. So, theta is sometimes we write theta p, means that at this temperature this ferromagnetic material becomes the paramagnetic material. So, this theta p is basically we write theta p equal to theta c, although it is always it is not true, theta p slightly less than theta at this T c Curie temperature, okay. But its difference is very small. So, that is why we take theta p equal to T c. Now, today we will see about this, what is the relation between temperature and susceptibility of ferrimagnetic material, ferrimagnetic and as well as susceptibility for antiferromagnetic right. So, so C, this chi is basically for in paramagnetic phase chi in paramagnetic phase is C by T, and chi is nothing but m by h, or we write sometimes this way also mu 0 by b, whatever. Okay. So, ferrimagnetic and or ferrimagnetism and antiferrimagnetism and antiferromagnetism anyway. Okay. So, it looks clumsy, let me write here and antiferromagnetism. So, both are basically this antiferromagnetism is basically this special case of ferrimagnetism. So, you know this arrangement of these spins are antiparallel. So, in case of ferri, this spin magnitude or magnetization are not, magnetic moment are not same, they are different. So, we will get resultant moment, whereas in case of antiferromagnetism this moment of both parallel and antiparallel one, these are same. So, net magnetization becomes 0. Okay. So, this arrangement if it is just anti ferromagnetic or ferrimagnetic arrangement we can just draw like this. Okay. So, this way one can show the lattice of this ferromagnetic or antiferromagnetic spin alignment. Only difference, as I told this, in this in case of it is say antiferromagnetic, for ferromagnetic this magnitude will be different, this magnitude will be different, this magnitude will be different, right. This magnitude will be different, yes. Then it is, we tell this ferrimagnetic. Okay. So, now here this lattice we can think as a interpenetrating of two sublattice, right. So, this basically one can think about this, one sublattice is for parallel spin, right. Okay. Plus another one sublattice for antiparallel for down. So, this if I, so it is, if it is antiferromagnetic, so length will be same. Now, just for ferrimagnetic this length will be small, but arrangement are same. So, then I can this. So, okay. This. Okay. So, this if we tell the sublattice A and this sublattice B. Okay. In A side this spin up, okay, and B side spin down. So, we think this is this ferromagnetic or antiferromagnetic lattice crystal is basically where this arrangement of this magnetic moment is interpenetrating of two sublattice, one is for spin up, another is for spin down. Okay. Now, you think that if you take any spin here, so then according to Heisenberg model. So, there will be exchange interaction. Okay. This is spin, this is A site spin. So, from surrounding this from A site there will be interaction, okay, with this A site other spins, there will be exchange interaction, as well as from B site with B site it will have exchange interaction. Okay. Now, if you take from B site one, so exchange interaction with this B site spins as well as this A site spin. Okay. So, interaction here. So, if we consider this molecular field, Weiss molecular field, right. So, what was that? You have a spin and surrounding nearest neighbor, whatever the spins are there. So, they have influence on this. So, it is as if these some fields are there. So, interacting this spin with a field provided by the nearest neighbor. Okay. So, that you know that field, molecular field, that we took lambda in proportional to the magnetization, and this is the proportionality constant, molecular field constant, right. So, that we tell this molecular field say Bm. So, Bm is this. So, that Weiss field, mean field. So, here now we can think that way. So, for this, okay. So, molecular field from this A site as well as molecular field from B site. So, A site spin will fill the molecular field from A site as well as from B site, and vice versa. This will fill the molecular field from this site, B site as well as from A site, right. So, here, so in this lattice basically whatever this, if you take any spin either up or down, so it will fill interaction, it will there will be exchange interaction with the anti-parallel one as well as interaction with the parallel one. So, since anti-parallel one is the nearest neighbor, so this interaction, exchange interaction will be stronger than this from same site. So, this parallel they are not the nearest neighbor. So, that will be weaker. So, that molecular field for a spin at A site. Okay. So, here this molecular field we can write B molecular field on A site spin. So, that is from that we will take magnetization from A site, magnetization of this A site, and then this proportionality constant. Okay. So, this I am writing lambda A because it is A site and this interaction with this A site, magnetization from A site. So, this constant I am writing lambda A, and I am taking negative sign because we are taking here all our antiferromagnetic exchange interaction. So, that is what we are taking this minus sign, then plus on this A site interaction, that exchange interaction from the B site. So, that is again this whatever the magnetization of B site, I can write MB. Okay. Then this constant here interaction. So, A from B side. So, let me write lambda A B, okay. And again this negative sign, that exchange interaction we are taking negative. So, this will be the molecular field on A side spin, and similarly molecular field on B side spin will experience. So, that will be again it is from A side. So, magnetization is M A, that will proportional to the magnetization of this A side on B side. So, this is a lambda, it is on B side from A side. So, I am writing lambda B A, so negative sign, and then from B side on B. So, M B proportional to M B, and that I can write lambda B B. Okay. So, that will be the molecular field on A side and B side. Okay. So, you can notice now that M A will be equal to M B So, I think I do not need now this. So, see this B equal to this lambda A for say ferrimagnetic, M A magnetization of this A site is not equal to M B, okay, because their magnitude are different, their density may be different also, and but lambda A is lambda A in exchange interaction, the strength here is not equal to lambda P V, okay, because their magnitude are different. So, strength of interaction, exchange interaction may not be same. So, this say I am writing lambda A is alpha and lambda B B is beta, okay. And on this lambda A B will be equal to the lambda B A, because this is the interaction. So, this they will be same. So, this I am writing say lambda, this I am writing lambda, okay. So, for antiferromagnetic case, for this is for ferrimagnetic case, for antiferromagnetic, say for antiferromagnetic, so M A will be equal to M B, M A will be equal to M B, right. Then lambda A will be equal to lambda B B, okay. So, say this we are writing say alpha, okay, or whatever beta we can write. So, alpha, so this, so that means alpha equal to beta, that means alpha equal to beta, okay, in this case. And of course, this one again same, this one is again same, this lambda A B is equal to lambda B A, say it is lambda, okay. So, for ferrimagnetic case, so I can write B M on A equal to. So, now if we apply magnetic field, if we apply magnetic field, so then this total field on A side, so that will be B 0. So, applied field if it is B 0. So, okay. So, I will put later on. So, this one will be minus alpha M A minus lambda M B and B M A molecular field on B side, sorry, this will be B. So, that will be this will be minus lambda M B, sorry, M A minus this is lambda B B, means this is beta, I have written beta. So, beta M B, okay, beta M B. Okay. On the other hand, for this case, I can write B M A equal to in this case lambda A A, lambda B B both are equal. So, I can use just alpha or beta whatever, alpha M A minus lambda M B, okay, and B M B will be equal to minus lambda M A minus lambda B B, So, lambda B B is again alpha, okay, is alpha M B, okay. So, one can write M A equal to M B, one can put also M A equal to M B, yes, M A equal to M B one can put, but when we need we will put it there. So, now let us consider that this in paramagnetic phase, both are in paramagnetic phase, means at higher temperature T is greater than that transition temperature, that we will see there what is the transition temperature. So, there it is, they will be in paramagnetic phase, right. In paramagnetic phase, what will be the chi that we want to find out, what will be the transition temperature that we want to find out. Okay. So, in this case, so for simplicity for this ferromagnetic case, for simplicity, let us ignore the alpha beta, alpha and beta is very less than, basically they are very weak, experimentally also it is found they are very weak than lambda. Okay. So, lambda is very strong interaction between, because as I told you they are nearest, they are neighbor, okay, anti-parallel neighbor. So, if we consider this one, so what you will get, that B you will get in this case P M A equal to minus lambda M B and B M B you will get minus lambda M A, okay, minus lambda M A. So, in paramagnetic phase, T is very high, at higher temperatures, that is paramagnetic phase, that is paramagnetic phase. So, in paramagnetic phase, so chi equal to C by T, that is valid, chi equal to C by T, that is valid, means M equal to C. So, we can write in parentheses M equal to M by B. So, I think one can just forget this mu 0. So, mu 0 one can take inside this C. So, I can write M B by or M by H by C by T. So, this will give me M T equal to C B, right, M T equal to C B. So, now I have two field, one is M A T equal to C B M A, right, C B M A, and another one M B T equal to C B M A M B. Now, here I have to write basically the C will not be same, in this case for ferromagnetic, in this case C will not be same, So, because this moment are different for A site and B site in case of ferromagnetic, but in case of ferromagnetic this C A will be equal to C B, because moment are same for both. And this mu here, this I have not written. So, mu that I think here I can write mu equal to or mu square equal to G J square J plus 1 mu V square, right, mu V square. Okay. So, in this case its Coulomb constant will not be same, C A and C B we have to use. Now, from here this you can put this BMA is, what is this? BMA is minus lambda MB, right. So, minus lambda MB. So, I can write here, so this side plus minus lambda MB. So, here I have to yes, for this, that is MB. So, I have to write here MB. So, I can replace this BMA by this, and BMB I can replace with this. So, minus, so this side I can take, I can write plus, then BM lambda. So, this lambda and that MA, this I can write MA, right. So, here you can see, so this I have to write equal to 0, right, and this equal to 0, right. So, now to get the non-vanishing solution for MA and MB, So, determinant has to be 0, right. So, coefficient of this M A M B, what is here T. So, determinant will be, so determinant will be T of M A and lambda C A, and this case M A, this lambda C B, and for M B that is T. So, this has to be equal to 0, right. So, from here what you can see that, so I can get here T square minus lambda square C A B square equal to 0. So, I will get this will give me T equal to square root of equal to lambda square root of C A C B, right. From here I will get this T equal to, so you cannot see, so I think I should write so this will give you T square equal to this square. So, T equal to lambda square root of C A C B. Okay. So, that will be the basically this is Curie temperature, for ferromagnetic case. So, for ferromagnetic case, what is the Curie temperature I got? T C equal to lambda square root of C A C B, right. Now, in case of antiferromagnetism, so as I told that C A equal to C B, so square root of C square, so is C lambda C. So, for this case, whatever this transition temperature will get, that is we tell this nil temperature. So, it is T n will be equal to lambda C. Okay. So, it depends on the exchange interaction constant as well as Curie constant, right. So, so for both cases we are able to find out the transition temperature. Now, one can show that if we do not neglect this alpha beta, if we do not neglect alpha beta, okay. So, one can show that this will be it's yeah, I think I will show you. So, let me if alpha beta is not neglected. So, for antiferromagnetic case we will show this what is the result, but for this case for ferromagnetic we will not show, it will be slightly complicated. So, that I will come later on. So, here why I want to show you that that basically if you so that will be more clear if we calculate the susceptibility. So, for susceptibility what we have to do? So, we have to apply, so susceptibility in paramagnetic phase we have to apply magnetic field, So, in that case so this we can write B. So, this if we write that magnetic field, the total field on this A side, that will be it is B A. So, that will be B 0 applied field plus BMA, right. And similarly for B side, B will be B 0 plus BMB, right. So, now one has to put BMA and BMB here, it is there. So, in this case also if we consider that this BMA is lambda MB, BMB is lambda MA. So, this you will get basically B 0 minus lambda MB, and in this case you will get B 0 minus lambda MA, right, minus lambda MA. So, I think so I think I can show you simply this antiferrous case. Okay. So, I have to go few step more, then I can show you the calculation. So, here so this is the your total field, that is this. Now susceptibility, to get the susceptibility, so that is basically chi equal to m by H or B, okay. So not B, it will has to be B 0, right. So, we have to take proper form. So, what we should do, so B A equal to B 0, this fine is now what is, so B A, so B A, what we will do, I can write this one, I can write chi equal to, this is fine, m. So, I think in case of MA, so this chi A, so this and this chi I will write, chi 1 can write C by T, because it is in paramagnetic phase, you know. So, this is C A by T. So, I can write MAT equal to C A, my applied field. So, so let me, I need space. So, let me use this space. So, chi equal to m by, so I can write this m equal to in general C by T in paramagnetic phase. So, for MA, this is MA equal to C A by T, no, so I am doing mistake. So, this is this MA I can write m equal to C by T, this is chi is C by T, so into B, right, magnetic field, because m by V equal to C by T. So, then I can write MA. So, for paramagnetic phase I can write chi equal to C by T. So, chi is m by V, okay. So, m equal to C by T into B. So, for MA I can write C A by T, and B is, I have to write B A I have to write BA, and BA is I can write this B0 minus lambda MB, BA I can write B0 minus CA by T, this lambda MB, right. Similarly, MB I can write CB by T, B will be BB, this one. So, that is B0, again this is B0 minus lambda MA, means CB by T, this it is a lambda MA, right. This I can write. So, from here if we add them, so you will get MA plus MB, that will be basically magnetized, total magnetization of the system M, that is equal to 2 CA no, it will be CA plus CV by T B0, okay, and here CA lambda by T minus lambda by T, okay, CA here CA MB and here CB MA. So, I have to write yes, I have to write this lambda by T, then CA MB. So, this I need space CA MB plus CB MA, right. Actually, I think what we should do, just we can replace this MB by this MB, okay. So, we can put this value here, this we can get put here. So, we will get MA, similarly we will get MB if we put this one MA here. So, I think that way I think I will just write the result, yes, I have calculation, yeah, just I will show you. Can you, I think here I need this one to show you this calculation. I think this I want to show you that. So, if you replace that one, then you will get basically yes. So, you see this MA. So, this multiplied by T. So, this both T are there. So, MAT. So, that is why I write MAT, okay. Or just here you can see MA equal to yeah, CA MA equal to CAT B0 right, minus lambda CA by T square, minus lambda CA by T square, from where this T square T is coming. So, here MB I am replacing by this one, okay, taking out T. So, MB I have replaced by taking out T, CB B0 minus CBMA minus lambda CBMA. Okay. So, just here I have shown you the calculation, okay. In every step I have shown, just you check it or you can do yourself, then you will get this MA and MB. So, M equal to MA plus MB, equal to this So, chi is mu 0 m by b 0. Okay. So, sometimes we write m by h or m by b 0, that depends on the unit, whether it is CGS unit or SI unit. So, this you are getting equal to this. Okay. So, this chi equal to this. So, this is for the ferromagnetic case. Okay. So, here you can see this chi equal to, it is not C by T minus theta or minus Tc in case of ferromagnetic. So, its dependence on temperature is different. So, I will show if we plot chi by 1 by chi as a versus of as a function of temperature, then you can see this it is different, its curve is towards the axis, So, that I will show you, and for antiferromagnetic case just you replace this C equal to Cb equal to C, then you will get from this formula you will get this. Okay. From this formula you will get this. So, here just I replace this with Contd constant, but it is its value is twice of this normal Contd constant. So, some constant I have put, okay, to keep the similarity. So, this is the susceptibility for antiferromagnetic case and ferromagnetic case. So, for ferromagnetic case, for ferromagnetic case, you see this temperature behavior is slightly different than this antiferromagnetic, ferromagnetic and this paramagnetic, where its 1 by chi versus temperature is linear, right. So, if I plot, so I will, so basically if I plot, so this is the C by T, okay, for paramagnetic, and then this is C by T minus Tc, right. So, this is Tc, and this so this is basically Tn, and this we write theta, sometimes p we write theta p. Now, its Tn and theta p, they are, what is theta p, that I will show you, they are not same, they are different, but sometimes they are same depending on the condition. So, if I ignore this alpha, and beta, then theta p equal to Tn. If we do not ignore, then one can show that this theta p is basically theta p, Tn and this theta p, this ratio, one can show Tn by theta p, it is equal to I guess lambda minus alpha divided by lambda plus alpha, this kind of things. If you ignore alpha, then they are same. If you do not ignore, then this Tn is so minus alpha. So, it is smaller, right. So, Tn will be, what is this? Yes. Yeah. So, Tn will be, if different from this theta p. So, that calculation, if we do not ignore this, alpha and beta. So, in that case you will get, I will show you, if I do not ignore. So, what will happen, just I will, okay, So, if I do not ignore, if I keep in case of antiferromagnetic case, okay. So, I am keeping alpha equal to beta. So, alpha I am keeping. So, if you just proceed same way, just I have shown here calculation, you can do yourself, then you can show that that T n equal to C lambda minus alpha. So, earlier it was C lambda, now it is C lambda minus alpha. So, if you put alpha equal to 0, C it is the other case. Similarly, if you calculate the susceptibility without ignoring this alpha in case of antiferromagnetic case. So, just you proceed, keep it. So, it is not it is not this, I think this one in paramagnetic phase. Okay. So, if you do not ignore alpha, keep it alpha, and same way you proceed, then what you will get, chi equal to, you will get C by T plus theta p. Okay. Now, where theta p is C lambda plus alpha or alpha plus lambda. Okay. So, T n whatever we have seen, that is C lambda minus alpha is not equal to theta p, equal to C lambda plus or alpha plus lambda. Okay. If you ignore alpha, then T n equal to theta p, C lambda, both are same. If you do not, if you consider this alpha, then they are different. Okay. So, that is what I told you. So, this is for antiferromagnetic case, antiferro. Okay. So, where C is T minus this plus theta p. Okay. So, I think I will stop here. I will continue in next class. Thank you.